I show ASI interconnect technology. And Guru was the second one in the line who was focusing mostly on the functional verification that the design guys are already done. So this is
Scalable. So
yes, uptime per cluster, and then the clusters, uptime clusters and 15 units per cluster.
He'll give a little bit of history a little bit later. We have the, Con worked heavily with a number of systems, plus a series of master theses. There are different versions. This is the later version where we have clusters. First version is essentially had one cluster.
So the current revision of WinC2R has a bus-based clustering design to support system scalability, where each cluster can support up to 15 functional units. The picture here shows a sample functional unit. A functional unit carries out a set of discrete operations on a block of input data to produce a block of output data. These set of discrete operations together are known as a task in WinC2R, and the programmers have the flexibility to define the task parameters to be executed on the functional units. The figure here shows how a sample interleaver functional unit interleaves a block of input data to have non-contiguous segments of output segments. So in order to look at the WinC2R programming model a little bit more in detail, the programming model provides us 3 tables to configure the properties of the tasks which can be implemented by the system. They are the global task table, which contains the task scheduling and allocation properties, the task description table, which contains the runtime execution properties of each task, and the next task table, which defines the flow between tasks as a producer-consumer model. How these tables are used by the system can be explained using a simple example. Consider a block of input data which is provided to the WinC2R system. It is now the function of the VFP controller to look at the global task table to identify which functional unit needs to process the block of data. It then schedules the task to the identified functional unit, which then refers to the task description table to execute the task. Once the execution of the task is complete, the functional unit sends a message to the VFP controller, which then looks at the next task table in order to schedule the next task in the flow. It can hence be understood that the processing of a task flow consists of back and forth interaction between the VFP controller and the functional units of a cluster which it is responsible for.
So the VFP is also a hardware, right?
Yes. VFP is a hardware.
Program for the table.
A high-level overview of the Mobile WiMaX protocol. The IEEE 802.16e standard is an amendment to the class of YMax protocols which supports fixed, mobile, portable, and nomadic wireless access. It's called the Mobile WiMaX protocol because of its support and vehicular speeds up to 75 miles per hour. The standard defines the physical and the math layer of the protocol, and some of the key features of the physical layer are that it supports duplexing in both time and frequency, and it supports scalable orthogonal frequency division multiple access for the following values of subcarriers at the following channel bandwidths. The picture here shows a typical YMax flow implementing time division duplexing. The YMax protocol dictates that the sequence of preamble, the frame control header, and the mapping messages followed by the data bursts must be strictly met, which means that these messages have to be triggered off one after the other in a sequence. In order to provision such a flow in WinC2R, we require tasks to implement each sequence, and they have to be executed one after the other in sequence. And as we've seen before, it is the function of the WinC2 of the VFP controller to schedule and activate the tasks. With a brief idea about the YMax protocol, we proceed to define the physical layer system design of the YMax protocol, which can be implemented by WinC2R for the transmission and reception of the MAC protocol data units. We have identified 3 main steps in the YMax transmitter module. The first is the generation of the map PDUs, and for this purpose we have defined a MAC, a processing engine, which provides units of data to the header engine, and the function of the header is to append the header to create the MAC PDUs. The next step is correction and protection encoding, which is carried out by a sequence of scrambler, Reed-Solomon encoder, convolution encoder, and interleaver. The final step is modulation and transmission, which has dedicated processing engines to do the same. The terms processing engines and functional units are used interchangeably. Functional verification. In this section, we explain the functional verification of the features we wish to test. And in order to define the scope and the focus of the work done in this thesis, we give a brief overview of WinC2R's history. So the WinC2R project has been spearheaded by Professor Fredra and Professor Zoran in WINLAB. The first revision of WinC2R defined an FPGA-based architecture with distributed VFP controllers, where each functional unit had a dedicated VFP controller. The work done by Khan, Prashanti, Sumit, and Tejasvi was to implement a proof of concept for the VFP design by implementing the 802.11a transmit receiver modules.
A few other students.
Quite a few. But that's okay.
It's okay.
And so the key outcomes of that work were twofold. The first one was they identified the VFP design as a potential use case to provision wireless protocol flows. And secondly, with this architecture of having dedicated VFP controllers for each functional unit, they noticed that most of the VFP controllers were in the idle state for most of the time. In order to provision better utilization of the VFP controllers, the second revision of WinC2R was proposed, which has the bus-based clustering design with shared VFP controllers, as we have seen. The work done on WinC2R revision 2 is as follows. The architecture and the design has been done by Omkar, who has defined the clustering-based architecture, and he has implemented the VFP controller module in System Verilog hardware description language. And the integration of the processing engines with the platform and defining the system flow has been done by Mohit and Madhura. The verification engineer for this project has been Akshay, who has developed an OVM-based test framework for WinC2R, and he has worked hand in hand with Omkar and Mohit and Madhura to provision proper task scheduling and activation, wherein they ensure the tasks can be programmed and executed on the system. With this work done, we had to address the following opens in order to really assess the functionality of the WinC2R revision 2. And these are the opens which have been identified, and in this thesis, our focus will be on the first three, for which we perform functional verification. And for the architecture scalability, we propose a design which could be used for future work. When we say we are concerned with functional verification of specific features, what we mean is that we implement test cases to answer the does it work question, and we do not deal with the timing as guarantees of the system for the protocol. So in order to address the three main features described in the previous slide, next task processing is the first feature we have identified, which consists of scheduling the tasks in sequence. Our functional verification goal here is to verify if tasks are scheduled and activated as per how it has been programmed in the flow tables. For system regulation, it is primarily concerned with data sizes which are being used in the task flows. And for this, WinC2R has two features called chunking and dechunking, which is the fragmentation and packing of data. And our verification goals here is to see if the data sizes in case of chunking are as per program, and in case of dechunking, if the recombination occurs and the next task gets activated after recombination. Finally, in order to provision different protocols, WinC2R's task has a priority-based task programming model where we can allot a higher priority to certain kinds of tasks. And what we wish to verify from our tests for this is to see if the activation is according to the set priority. Finally, we propose a verification plan for inter-cluster communication. So as we had mentioned, next task processing consists of scheduling tasks in sequence. What it really means in wireless protocol domain is that it signifies adherence to the protocol flow, and secondly, it guarantees the schedules and the quality of service for the protocol on the system. The verification goal for our functional tests here is to see if the tasks are activated as per the programming flow. For this purpose, we consider the following system of 7 functional units in a single cluster unit. In order to understand the next task processing flow in detail, we look at the interactions between the functional units and the DFP controller. When a functional unit has completed the processing of a task, it stores the output data into its output buffer. At this instant, it sends a command termination message to the VFP controller indicating that it has completed task processing. Now the command termination block triggers the consumer identifier block to identify the next consumer or the next functional unit which has to process the next task in the sequence. This refers to the next task table to identify the consumer functional unit and triggers the data transfer initiation unit, which triggers the consumer to pull the data from the producer. The DTI unit then sends a control message to the consumer functional unit, which then pulls the data from the output buffer of the producer into its input buffer through the AXI bus. At this juncture, the consumer functional unit sends a message to the task insertion unit saying that it has the task, the input data to perform the task, and the VFP can schedule the task. Now the task insertion unit sends a message to the scheduler, which then activates the task on the consumer. This whole process continues in sequence as producer-consumer interactions in the system until the end of the task flow. In order to verify features like these, what we require is an entity called the test bench, which mimics the design in which the environment in which the design will reside. For this purpose, an OBM-based software test bench framework has been defined, where OBM is an open source System Verilog based class library, which provides a standard verification methodology. The test plan for verifying the next task processing feature is as follows. We wish to test the VFP controller as a black box, which means that we are not looking at the internal features which flow between the scheduler, consumer identifier, and so on. But what we are really looking at is when the tasks are activated and when the tasks are completed. For this purpose, we have defined 2 specific monitors called the task activation and the command termination monitors, which are instantiated at each functional unit, which decode these control messages as and when they are sent between the VFP and the functional units. We have also defined a global scoreboard which keeps track of all these monitored outputs and compares them against the reference programming model to verify if the tasks scheduling and activation is according to the program flow. In order to implement the scoreboard functionality, we need a reference lookup table to match the activation and termination messages. And for this purpose, we have identified three parameters which can be used to do the same. When a task is activated, the task activation message contains a unique task pointer for the particular task. And the command termination message contains a unique ID for the functional unit and the task which is being processed. And based on the programming flow, by defining a table which lists all the task pointers and the next task parameters, the scoreboard has a reference to match all the messages it receives from the monitors. So the functionality of the scoreboard is to buffer all the incoming task pointer messages, and whenever it gets a command termination message, it tries to match the task ID and the FU ID with the task pointer to see if this pertains to a task which has already been triggered before. And when a match is found, then the particular value in the buffer is flushed out. So test results can be understood when at the end of the simulation if the buffer of the scoreboard is empty. And for this purpose, we have considered 2 cases of next task processing. The first one is a sequential task process where each task is followed by one next task. And in such a case, we have simulated cases with 10, 20, 50, 100, and up to 1,000 tasks scheduled one after the other. And we have successfully verified that in all these cases, the next task has been processed according to the program flow. The second case we have considered is a task forking multiple next tasks. The WinC2R architecture has defined that each task can fork up to 16 next tasks. However, our test cases have identified a bug in this feature, wherein when multiple next tasks are forked off, only one task gets activated. The scoreboard functionality for these tests were extended by adding more fields for the command termination message in the lookup table.
So why is it important to have a fork?
This is to provision cases where in a typical protocol flow, when a data is obtained from the MAC to the header. So that will be the time when the preamble message has to be processed, so that by the time the preamble is transmitted, the data packets are ready to be transmitted. In order to provision complex flows and meet the timing requirements in the long run is why the forking next task feature has been designed. WinC2R's task model supports two kinds of tasks in order to provide priority-based scheduling in the BFP controller. The two types of tasks are known as synchronous and asynchronous tasks. Synchronous tasks provide deterministic guarantees. They have a fixed start time and they have a set guard time in order to ensure that the tasks are activated at the required start time. And they can also be recurring and by having a rescheduled period after which the same task is repeated again and again on a particular functional unit. And the other kinds of tasks are asynchronous tasks, which are scheduled on a best effort policy, in the sense that they are scheduled as long as they do not collide with the synchronous tasks' time requirements. Fragmentation and packing are two features implemented in YMax for runtime systems regulation. Fragmentation is a process of dividing a MAX service data unit into one or more fragments, and packing is the process of combining several MAC SDUs into one huge data payload. WinC2R architecture has inherent support with functionally similar features in the BFP controller called chunking and dechunking, which can be potentially used to implement fragmentation and packing. Chunking is a mechanism of splitting a block of input data and processing each block as an individual task. Now, WinC2R architecture defines that chunking can be implemented only on sync tasks. Chunking feature has been introduced in the architecture in order to improve overall end-to-end latency of the system. The animation here shows how a sample chunking task is processed. So each chunk, as we can see, D1, D2, D3 is processed as a separate task, and the flow is continued by all the processing engines in the field. A potential use case for the chunking feature is that it could be done in the MAC processing engine of the transmitter to implement fragmentation. Our verification goals to verify the chunking feature is to see each time a chunk task is activated, what is the data size the task is working on. And in order to get information on the data size of the task, we take a closer look at the scheduler part of the VFP controller. Whenever a task is inserted into the scheduler, it goes into one of the 15 task scheduler queues. So the VFP controller scheduler block has 15 task scheduler queues to support 15 functional units in a cluster. And each task scheduler queue has properties pertaining to the task which needs to be activated next. Whenever it's the correct time to activate a task, the TS queues send a message to the task activation unit containing all the parameters of the task. In case of a chunking task, the parameter which we are interested in is the current chunk size. Hence, we have identified monitors which could be instantiated at the interface between the task scheduler queues and the task activation unit to decode the size of the current chunk being processed.
So is there a higher level model for any of these that you are comparing against, or is it purely, with Verilog you are?
It is pure, in the sense the
Like, some of the blocks that you showed before, like the encoder and things like that. For that, obviously you need a higher level model.
Right.
Architecture level model.
So what we are using here, so there are two types of processing engines which have been defined. So one was the work done by Madhura, where she defined the real processing engines, where it actually implements the task of, say, a modulator to generate INQ samples and so on and so forth. But since we are dealing at an architectural level, we have the dummy processing engines, where we have programmed the input and the output data sizes and a fixed number of clock cycles it needs to wait before it provides the output data. So it adds zeros to the input data to produce an output data of the required size. And so we use like a more simulation level model in order to verify each of the processing engines, since we are trying to verify the VFP architecture and not the functionality of the processing engines.
But I just want to point out that VFP was implemented RTL in System Verilog.
Right, okay. So even for VFP, there is no like to do the scheduling and things like that. If there was any higher level model.
No, that was in pure RTL.
Pure RTL.
This is the pure.
But some of the PEs were implemented in RTL too. Some of them, like modulator, I think.
Modulator and interlevel were implemented in the RTL. And well, for some of the other features, we have these dummy processing engines.
Because for certain things, you will need a higher level model, right?
Your scoreboard is in a way in a higher level model. You actually insert the expectations in the scoreboard, right?
Right. So I insert the parameters which it needs to look for. So when I program each task, I say for every task, these are the parameters for the next task. And so the scoreboard decodes the actual messages with the task pointer and then buffers them, and it compares them against what the command termination of the next task is. So those are the real values at the runtime, which are matched against what was actually programmed before the simulation was started.
And the test bench, is it mainly for VFP, or like you had a big system, but the verification is mainly targeting the VFP portion of it, right?
Yes.
The VFP features, but he's actually looking at the whole system of the set of engines and even the set of clusters.
Okay.
But he's exercising the PHP-related features, like his tasks, scheduling, and so on. He doesn't look into the encoder, decoder, and all these other rate-and-rate functions. There's not one-time back simulation relation.
It's a patchwork of different looks. Some of it we've done in RTL, some like I think Madura has some C models, right?
For the engines, yeah.
For the engines. Depends on what which.
So the engine is actually the combination of the hardware, the C models, and we even have the Centric processor as one of the engines, and doing the interleaver, minor decoding, and so on.
Yeah, because for those definitely you need a higher level.
For those you need to get. So this is the work of others in kitchen, my understanding, for the next set of VFP-related features.
So in our test cases, we have defined flows with the following values of the data chunk sizes, chunk size, and the first chunk size. The thing to be noted here is that the WinC2R architecture supports a different value for the first chunk size in order to provision preamble messages of different wireless protocols. And another thing to be noted is that when the last chunk needs to be processed, after the first chunk and the number of chunks of the chunk size, whatever is the value is processed as such, the last data, and it's not padded to make it as big as the chunk size. So using our task scheduler monitors, which monitor at each instance of the chunking task, what is the value of the data being processed. We have successfully verified for all these above 3 cases, which are random test cases we have considered in order to verify the proper setting and reading of the chunking values and the chunking tasks in the VFP controller. We have also verified the activation and termination of all the tasks which are set up as chunking tasks as part of this verification effort. Now, dechunking is a feature of recombination of the chunks of data. The basic premise for dechunking is that once a chunking task has been set up, several number of each block of data is being processed as a different number of tasks on different processing engines. So dechunking tries to regulate the system by combining all these chunks and processing them as a single chunk of data. The VFP controller is the controlling unit which takes care of dechunking. And the animation here shows how a chunking task is first set up, and for the unit implementing dechunking, the next unit in the flow waits until all the chunks are obtained and then processes them as a whole. In case of our YMax setting, dechunking could be potentially used as the math processing engine to implement packing of combining multiple service data units. So our test code was twofold. First, we set up a chunking task which has been verified using our chunking test. The next thing is that by setting the dechunking flag, we want to see if the next task gets activated only once in the flow. And this was verified using the task activation monitors. Our verification tests for this feature exposed a bug in the design, and the bug can be explained in 2 different scenarios. In the first scenario, when the number of chunks is 2, the functional unit implementing the dechunking feature its task gets triggered only once, when it is supposed to get triggered twice, and only the next processing engine should process the task just the one time. And when the number of chunks exceeded 2, then the tasks were activated prematurely and the dechunking feature did not occur. So this has been discussed with the architect and the designer, and it has been classified as a bug for the design improvements. We've seen in the previous slides that WinC2R supports 2 kinds of tasks, the sync task and the async task. And the sync task has deterministic guarantees by having a set start time, guard time, and a rescheduled period. So from this, the question arises as when a functional unit has both a sync task and an async task to be processed, which one gets activated first? Or in simpler terms, is the sync task always given priority? The short answer is no, in order to provision better utilization of both the VFP controller and the functional unit. So each time there is a clash of a sync task and an async task waiting to be activated, the VFP evaluates the following parameters A and B, and based on that, it determines which task needs to be activated first.
In the context of YMax, do you have any sort of intuition where is the async task, where is the sync task?
So in terms of YMax, the first, considering we are implementing a time division duplexing system, in that case, the scheduling of the sequence of the preamble and the controlling messages and the mapping messages, all those must be programmed as sync tasks because they have to go on first. But then the data bursts can be programmed as async tasks since they are scheduled on the best effort policy, as in a given time window, how many ever data frames can be sent.
As long as you can make sure that the specs are satisfied, best efforts. Yes, we still satisfy the QoS, the requirements of the spec.
Right.
So I'm not so sure that you can really do best effort there. I mean, you can have best effort if there's a buffer or a buffer of time. At the end of the day, you still have a sequence of things that you have to do in time.
It also depends on the loading of the whole system.
Yeah.
If it's unloaded, you essentially have all the bandwidth for the processing resources. So just use the one task that is synchronous to make sure that it gets synchronicity. But it's still accomplish it in time. If you have more,
If you have several protocols and some of them.
yeah, then it's very difficult decision. Then you have to play with the scheduling scheme. You have to come back from the PhD and then solve that problem.
I asked already, so you want to.
Soon Tom can be your advisor.
If I pass to qualify.
That's the most complicated one. Scheduler is the
Multi-dimensional.
So the verification goes behind the priority scheduling of the tasks, where you set up two different tasks, one of synchronous type and the other one of async type, and vary the parameters of the sync tasks and to see which task gets activated first. So in our test case, we first schedule a sync task and then schedule an async task. And based on the rule, if the async task can be processed before the start time of the sync task, then it gets scheduled first. So with this premise, we have considered three different test cases, wherein in the second case, due to the large value of the guard time and the start time, the async task got activated first, and in the other two cases, the sync task was given priority. The activation messages were again read using our task activation monitors implemented in the inter-cluster communication. Now, WinC2R supports a clustering-based technique, which is a bus-based cluster. And clusters can be designed based on two different design parallel lines. One is function, and two is based on performance considerations. When we look at a functional cluster, a group of processing engines implementing encoding, like the Reed-Solomon and the convolution and the interleader and the scrambler, could potentially be grouped together as one cluster in order to support several different protocols based on the requirements, since they are programmable. And the other use is based on performance, where if we have computation-intensive functional units in a flow, they can be scattered across different clusters in order to maintain or mitigate the latency in the system. So a typical complex protocol flow could span across functional units in different clusters, and which means that the task flow should happen between different clusters. And for this purpose, the WinC2R architecture defines the inter-cluster mechanism. Since WinC2R has a bus-based design, the architecture defines an outgoing mailbox at the VFP controller in order to take care of inter-cluster communication. We set up a typical test case considering a system as shown here. We have a functional unit N belonging to a cluster 1 with a VFP controller 1, whose next task should be executed by a functional unit M belonging to a cluster 2 having VFP controller 2. So when N completes processing, it sends a command termination message, and the consumer identifier block looks at the next task table and identifies that the next task should be processed by a functional unit in a different cluster. At this juncture, if it were an intra-cluster communication, it would write to the DTI block of the same VFP controller. But in this case, it needs to target the DTI block of the next cluster, where it sends the control message to identify the output buffer of the producer and the identified consumer. So the CID block now writes the message to the outgoing mailbox, which then arbitrates for the AXI bus and writes that message to the DTI of the identified consumer VFD controller. Now this DTI block then sends the DTI control message to the identified functional unit, which then takes care of data transfer. The thing to be noted here is that considering that the system interconnect is AXI and all functional units have an AXI interface, the data transfer mechanism is functionally similar in both intra-cluster and inter-cluster cases. In order to understand the intercluster better, let us consider a sample flow of tasks between FUs 1 to 2, 2 to 3, and 3 to 4. So the case of intercluster communication happens when FU2 finishes processing. So upon its completion of processing of a task, the first thing which needs to be taken care of is the transfer of control from VFP1 to VFP2. The second step which needs to be taken care of is the data transfer from FU2 to FU3. And the third thing is the task activation in FU3 by VFP2. The point to be noted here is that implementing a multi-cluster system is a non-trivial task. And owing to time constraints, we have decided to propose a plan for intercluster communication, which can be used as a reference for future work. In order to simplify the intercluster communication paradigm, we have approached the mechanism in a two-step process. In the first step, we program a cluster with the next task table indicating a task in a different cluster. And in this case, when FU2 finishes processing, then the consumer identifier must write a message to the mailbox, and the mailbox should try to arbitrate for the AXI bus. If this functionality happens in the system program as cluster 1, then we can verify that the mailbox mechanism works. The second step which needs to be taken care of is if the DTI block, the input buffer, is directly provided data by the test bench, then does it activate data on the activate the task on the functional unit which it is responsible for. And in order to do this, we program the same cluster as cluster 2, and using the test bench, we write into the DTI block. And we monitor the DTI messages on FU3 in order to verify if the control handoff has occurred successfully. So from our functional verification efforts, we have targeted 4 specific features of the VFP controller. First one was the next task processing, where our verification successfully identified that scheduling of tasks in sequence occurs, and we have verified that.
So the intercluster is future work?
Yes.
Okay, just make sure. So I didn't see it in your slides. What did I miss it?
So I put it in the next slide by mistake. And our tests have exposed a bug in the design where the forking next task mechanism does not work. And for cases of chunking tests, the tests have verified that the chunking values and the flags are properly set and read, and tasks are activated according to the program chunk sizes. And for cases of dechunking, our tests have verified that the feature does not occur, and the bug has been traced with the designer. And priority scheduling has been verified by scheduling tasks with different runtime properties, and it has been verified that the rule has been adhered to by the VFP controller to schedule tasks. The main takeaway from the efforts on functional verification is that WinC2R's task-based programming model is an elegant solution to provision protocol flows as producer-consumer interactions, because the programming model for any protocol flow is primarily dependent upon the flow and the runtime parameters, which means it's a standard programming model for multiple protocols. As a part of the future work, we have identified the intercluster communication feature, which gives a feedback on the system scalability. We also proposed that the current test bench can be migrated from the OVM-based methodology to the UVM-based methodology, which is the growing industry standard. And the UVM has additional specific features like a heartbeat mechanism, which monitors how much each verification components are being used, and it monitors their liveliness. And it also gives better report handling and callback mechanisms. And OVM to UVM migration is also supported very well by having open source scripts which convert the code from OVM to UVM. The next a few steps in any typical project like this are FPGA-based emulation verification to identify if to put the system to test in a real-time scenario and identify if the system behaves as programmed. And finally, to define the power numbers of the system to see if it provides optimum support to implement the modern protocols. A list of selected references. These are the references of the work done by Professors Suran and Frederick and the others in the WinC2R team for VFP and WinC2R.
When you mentioned some power numbers, what do you mean, like energy power? Is that what?
By that I mean the voltage and the power requirements of the system.
That has to be based on the actual implementation, right? Like what technology you are implementing.
Right. And so that will be the follow-up step after the FPGA-based emulation and verification is done. These are other selected references from the prior thesis on the revision 2 WinC2R architecture and some selected work on Mobile WiMAX, which was used as a reference to provide a base draft for the WinC2R design.